Alrighty, team. It's our last problem today, and it's an extension problem right from the get-go. Just basically a question for you to have a play around with. Um, you're not necessarily expected to finish the thing. I mean, I just want to be honest with that, but just to basically play around with some maths and see what you can come up with. Um, See whether our guest presenter thinks down the same track as you and tries the same things. So then tomorrow, obviously, we're back to school, but it's not really school, is it? Um, I hope you're excited as well as I am to start on with the differentiation topic. Hopefully, you've enjoyed these videos, and by stealth, I've managed to teach you a bit of complex numbers. So hopefully, you found them engaging. But as always, feedback appreciated. But let's crack on to today's problem. Our last one, 19, the beautiful prime number that it is. Alrighty, prove that trig expression there is a root of the irrational equation below. So I'll let you have a go at that. Like I said, just try some stuff. Just see what you come up with. Alrighty, solution is going to be provided by Hamish Jelleyman. He left MAGS at the end of 2015. He did incredibly well in the scholarship course, and he went on to university to do mathematics. And along with his twin sister, who also obviously left MAGS the same year, they both love maths, and Hamish is very enthusiastic to present this. So enjoy.
Hi, I'm Hamish, and today we will be looking at this problem here. There's two parts: a value we put in for x, and an equation we're putting in. And the question is, can we prove that this equation is true for that value of x? The first thing I tried when I did this question was I tried brute forcing it. Now, you can see some work in here. I skipped a lot of the messy steps, but essentially, if you factorize, expand, all that stuff, you end up with this equation here. This particular cubic, if you put it on a computer, do a whole bunch of stuff with a calculator, you can find that takes the value of x that were provided on the question. The only trouble with this is that, well, there's all these squares, the trigonometric functions. It's messy, it's horrible. Not a fun time. Doing it by hand is not worth thinking about. You try simplifying it by using trig identities. That also doesn't work because we've got all these powers that are messing things up. You've got to the power of 8, you've also got things you could do double angles. You give it a go, but it ends up taking pages and not getting you anywhere. In fact, this is really the simplest form of x that we have, so we'll use it for now. So instead, we want to break the problem down into manageable steps. So we do this by rearranging the equation once and then looking, what does it have that we can use to our advantage? Well, it's got this sort of recursive nature to it. So we're looking at this equation here. We see there's this -4 and the squared, and they keep alternating and turning up. So what we do is we define consecutive values of x by 4 minus the previous value squared. And so bear with me, what this does is it simplifies the equation all the way down until we get our first value of x is equal to our last value of x. And so what we need to do is show that each of these equations is true, including the last one. Luckily, we know a possible value for x naught, so we're going to give it a go. First, I want to mention something on complex numbers, simply that we're going to have this number c, complex number, the I being the square root of -1. We're using the angle pi over 19 because this complex number is, well, firstly, it's a solution to this equation. Omega to the 19 equals -1. C to the 19 equals -1, but also because when you do to the power of something for a complex number, instead of multiplying the number by itself or whatever, you just add a multiple inside the fraction. And this is great because when you use c to the n plus c to the minus n, it comes out to be 2 times cosine of n pi over 19. Using this, we can construct a polynomial here. You see on the screen that when you put the value of c in, you get our solution for x. So now, what if I proposed you that the value for c, p to this of c times p to the squared of omega to 4 equals 4. This is complicated and requires a bit of math. What I'd recommend doing is taking these two equations and in your own time working through the algebra to prove to yourself that this is true. One thing to note is that if this is true, then c is a possible value of omega, and because every value of c to the n where n is an integer satisfies the first equation here, you know it's true for all values of c to the power of n. And so if we work it through, we know that this is true, and all we have to prove at this point is that x3, the last one, is equal to our first one. So p of c to the 64 equals p of c, our initial value. You can do this. So you find p to c to the 64, you simplify it as much as you can, and then you put it in our equation, you get 3 cosines, you simplify it.
So, as you've probably realised, that's an example of perseverance. Hamish worked on that for a couple of days. He tried a whole heap of different things. He came back to me a few times and said, "Look, I've tried this; it's not going anywhere. I've tried something else." Now, if you Google the problem, you'll find some solutions on the net. They don't actually make a great deal of sense. Some of them, I'll be honest, it's quite a difficult problem. And this came from an extension worksheet I also found on the internet. This problem here was later down the sheet. Looks very similar, but obviously the twist being it goes to an infinite sequence of things. Look, I'm just posting this here as an interest sort of thing. Some of you may wish to explore it, but other than that, that's the end of this little series. Free to you, to your homes. I should put it on Netflix, shouldn't I? No, I shouldn't. Maybe I shouldn't. All right. Catch you tomorrow.